Hello, and welcome back. Today, I want to continue looking at transistor amplifier topologies by analyzing a two-transistor arrangement, the cascode. In a nutshell, this is just a combination of a common emitter and a common base amplifier, but the interesting part is that it does manage to combine the main advantages of the two circuits without bringing too many issues. So, if you're curious about this circuit and much more, then keep watching. So let's start off by looking at the building blocks. Two of the fundamental transistor arrangements are the common emitter and the common base amplifiers. The common emitter has a signal input through the base and output through the collector, while keeping the emitter common for the two signals. It features high gain, both current and voltage, but it does lack reverse isolation, mainly because of the collector base capacitance, which feeds back the inverted signal from the output directly into the input. This also has an adverse effect on bandwidth, which again is limited. At high frequency, this feedback path completely blocks gain. Now, in contrast, the common base amplifier has the signal input through the emitter and the output through the collector, and crucially, the base, the common pin, is usually kept at a fixed potential. This greatly improves isolation between input and output, and since there is not a lot of reverse feedback, the transistor is also capable of working at higher frequencies. The main downside of this amplifier, however, is the limited gain. Current gain is unity, or well, a bit less than that, so it just has voltage gain. Now, if you simply combine the two amplifiers, take the output of the first one and connect it to the second one, you do get a combined structure with high gain and you do get high isolation, but what you will not be getting is a high bandwidth. It will be limited by the first stage, the common emitter. So simply interconnecting the two is not all that useful. So the design you will however find is the subject of today, the cascode. This takes the common emitter amplifier and directly on top connects the common base stage. So by total component count, we have 3 less, but crucially, we have slightly different properties as well. So again, we are getting a high gain value, mainly from the common emitter part, and we will get good isolation, mainly from the common base part. But to understand the bandwidth, we need to remember what the initial problem we had actually was. The signal in the collector was being fed back into the base. By using the common base bit, the base is at a constant voltage, and through the base emitter junction, we end up having a very small voltage variation. So we can make the simplification that the emitter of the upper transistor and the collector of the lower one also has a relatively constant voltage. Therefore, there is nothing to feed back into the initial base to ruin the bandwidth. So because of this, the cascode arrangement does feature a high bandwidth, higher than the original common emitter amplifier. Now, long story short, the cascode combines the advantages of the two initial amplifiers. And as downsides, it's more complicated, there are more components than in a single transistor amplifier, and it needs a higher total voltage to operate. Both transistors need their collector-emitter voltage. So it's a fair trade. Now, before moving forward, let's just check these claims in the circuit simulator. For this analysis, I ended up making quite a few circuits, so let's move through them one at a time. This is an AC type of simulation, and the main objective is to observe the voltage gain and the bandwidth. To begin with, I constructed a common base and a common emitter amplifier around the same transistor and using the same operating point. The only difference is the signal source, which for the common base I used a 5 ohm series impedance, whereas for the common emitter it's 50 ohms. For the load, it's always 50 ohms. Now if we run the simulation and we look at the output, so the common emitter and the common base, we get more or less what we expected. The gain of the common emitter amplifier is larger, but the bandwidth of the common base emitter is higher. This is highlighted by the high frequency corner. Now, if we combine the two into a cascode, So the circuit uses the same transistor again and double the supply voltage. And while the operating point, so the current running through it at least, is more or less the same, well, for the bipolar implementation, we are getting a similar gain value as the common emitter amplifier, and the bandwidth is marginally better. For this implementation at least, the bandwidth improvement isn't that obvious. Now, another interesting aspect is the collector-emitter connection. While we would expect a rather fixed voltage here, we can see that it's almost the same amplitude as the incoming signal generator. So to be fair, it's smaller than the regular common emitter, so what we got with our first circuit, but it's not really a fixed point. The other comparison I wanted to perform was more or less the same, but with a different transistor type, the field effect transistor. So for this, I built a common source and a common gate amplifier around the 2N7002 found in the library. And then I also combined the two circuits into a cascode, again keeping more or less the same operating point in between the various circuits. If we look at these results, we can again see a clear difference in the gain and bandwidth between the first single transistor amplifiers, but if we look at the field effect cascode, we see the proper improvement that we were expecting. The gain is similar to the common source amplifier, and the bandwidth is similar to the common gate amplifier. I guess that with field effect transistors, the drain gate capacitance, also known as the Miller capacitance, is far more detrimental, and creating the cascode setup does make a more clear improvement. The last circuit to highlight is a hybrid, field effect common source and bipolar common base. This is sometimes implemented when you wish to get the best of each transistor type. If we look at how this thing behaves, we are getting similar performance to the all field effect amplifier, though with a very slight bandwidth improvement. But the important aspect to observe here is that the global gain is mainly impacted by the low side transistor. This, in combination with the output load, sets the amplifier gain. Now, another interesting aspect of this implementation is just how well the node in between the two transistors is stabilized. So both the field effect implementation as well as the bipolar transistor implementation had roughly 0 decibels in between the two transistors. But if we look at the hybrid, we are getting a very clear improvement of about 20 decibels. So by using the bipolar transistor on the upper side, we are far better stabilizing the lower field effect transistor. So the reverse feedback, the Miller effect, should be minimized. So the amplifier does seem to work. We are getting a combination of benefits, which is mainly highlighted with the field effect transistor implementation. Next, let's analyze the isolation properties. For this set of simulations, I kept the exact same circuits as before. I just swapped the location of the signal source and the load. So now we're injecting signal from the output and measuring it on the input. The connecting impedance value and supply were all kept the same. So if we run the simulation and we start looking at the bipolar circuits, we can see that the common emitter seems to be better than the common base at low frequency, but the roles reverse at high frequency. But if we plot the cascode, well, things are just all around better. Turning to the field effect implementations, we have a far more clear separation. The common gate is better than the common source. There is no frequency dependent reversal observed. And while with the cascode, this is again better than the individual circuits. Finally, if we compare the three cascodes, the bipolar, the field effect, and the hybrid, in these examples at least, the bipolar seems to be the better one, followed by the hybrid, and then the field effect. In practice, such a circuit will of course be impacted by the exact layout, but in general, you should expect the cascode to be better than the individual transistor amplifiers at reverse isolation. Now, the last thing I wanted to do today was actually try such a circuit out. See if the properties observed in the simulator actually translate to the practical design. For this, I built a slightly modified version of the hybrid Cascode. So the actual circuit I built has a 2N7000 NMOS on the low side and a BC547 on the upper side. I will be supplying this from 16 volts, and with the circuit at hand, we should expect a relatively modest gain of about 6 decibels, so it's not a lot, but it's something, and a very decent amount of reverse isolation, so at least minus 70 decibels at 100 MHz. So let's now see if these two parameters actually hold up in real life. To perform these experiments, I first connected a VNA to both the input and output of the circuit and supplied it with 16 volts. So the idea was to measure first the forward gain and then to swap the ports and measure the reverse gain. For these measurements, I used a PC connection just to get more measurement points and use a logarithmic display. Looking at the results, I first measured the forward gain. Here we were expecting about 6 decibels of gain and, well, got a bit more. However, the value is a bit unstable. The main culprit of this is the lack of matching between the measurement equipment and the amplifier, which is evident, at least on the input port, from the S11 parameter. So the amplifier we're measuring is nowhere near 50 ohms. So we are getting quite a bit of reflections on the input signal side. Moving on to the reverse isolation, here on the low frequency end, we are getting very high values, so the measurement equipment is not able to measure below minus 80 dBs, but the actual value is most likely a bit less. However, as we move to higher frequencies, the isolation sharply decreases. While this decrease is expected also based on the simulation, we should not be getting such small values. I mean, the simulation is predicting about minus 60 decibels at 200 MHz, and we're in the minus 30 decibel range with our practical circuit. To improve on this, one of the things I thought of was the actual transistors, and specifically their pins. They seem a bit large and could provide capacitive coupling in between them. So I cut them, made the transistors connected as close to the PCB as possible, and with this modification I remeasured. While this did not make a massive difference, it was still non-negligible either. At high frequency at least, the non-ideal effects of the physical parts did get reduced, so the reverse isolation improved by a few decibels. This made me think that the problem was not the schematic, but rather the practical implementation. So one more thing I tried was to double up on the large through-hole capacitors with some small low ESL ceramics. I added these in 3 points, one in the emitter, one on the base, and one on the supply. Remeasuring like this did provide a small benefit again, mainly on the high frequency bit. So while I did not get the huge isolation predicted by the simulator, these small improvements did prove that a lot of the performance lies in the implementation. A bad build will give bad results. Last thing to look at is where could you find cascodes in this day and age, and in what shape and form? Is this circuit still relevant today? So, first thing to mention are dual gate or tetrode MOSFETs. These are single package high frequency transistors that work similar to a pair of separate components configured as a cascode. So in most of these cases, if you look at a typical application, you will see one gate kept at a fixed potential while the signal is injected through the other gate. Now, while you will see this sort of component in old circuits, and you might still be able to buy some new, I'm honestly not sure if these are still being manufactured though. A more up-to-date topic though are high-frequency low-noise amplifiers. So I came across this paper discussing various low-noise amplifiers used for GPS signal amplification, so around 1.6 GHz, and while each of the amplifiers analyzed is being detailed a bit, In the final overview, we can see that quite a lot of these are cascode amplifiers. These include both field effect as well as bipolar designs. So this is quite a nice paper if you're looking for real-life amplifiers designed as cascodes. In the end, while the cascode circuit does provide genuine benefits, as with other high-frequency circuits, the details are everything. While it does add complexity, the benefits of the cascode, mainly the improved bandwidth, make it an invaluable tool even to this day, and it sees widespread use, especially in field effect transistor circuits and in the IC space. But that doesn't mean you can't build your own discrete amplifiers with success. So with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.